Good morning, good afternoon, good evening, and welcome to AI for Good. We hope that all you and your families, your friends, and your colleagues are all keeping healthy and safe. My name is Guilherme Martinez Roura from the ITU, the International Telecommunication Union, and it is a privilege to introduce today's session. ITU is the United Nations Specialized Agency for Information and Telecommunication Technologies, and we are also the organizers of AI for Good, in partnership with 40 UN sister agencies and co-convene with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the Sustainable Development Goals and scale those solutions for global impact. We are pleased today to discuss robotic exploration of subterranean worlds. This is part of the AI for Good programming track, where we discuss the role of robotics in achieving the UN SDGs. But before I introduce our moderator today, let me begin with a couple of housekeeping rules. Your microphone has been disabled, so please only use the Q&A and chat functionalities to communicate, which you can find at the bottom of your screen. Please make sure to set the chat message recipient to all panelists and attendees, and not just to all panelists. You can select this just above the message box. We have a distinguished set of panelists today, but as always, we are counting on you, the participants, to help create a very interactive session. So without further ado, I would like to introduce our great moderator today. Her name is LJ Reed. She is the BBC Click presenter. LJ, welcome, and the show is all yours.
Hello there. Thank you so much, Guilherme, for inviting me, and welcome everybody to the very first AI and Robotics for Good of 2022. It's a pleasure to have you with us. My name is LJ Rich, AI music artist and BBC TV presenter, and it is my honour to be your moderator for this webinar. Now, the DARPA Subterranean Challenge explores the potential for subterranean robots. And if you're joining this session, it's likely you'll have an idea of how important it is to be able to navigate underneath the earth, from cave networks to urban infrastructure, from search and rescue to subway systems. If you're wondering how machines are going to help with this, wonder no more, as in today's session, we're going to do a deep dive into the fascinating underworld of subterranean robots. And I won't be doing this alone, as you know. Our amazing panelists will be Dr. Timothy H. Chung, Program Manager for the Offensive Swarm Enabled Tactics Program and the DARPA Subterranean Sub-T Challenge, Dr. Kostas Alexis, full Professor of Robotics at the Department of Engineering Cybernetics at Norwegian University of Science and Technology, that's the NTNU. Dr. Navinda Kotage, Group Leader of the Robotics and Autonomous Systems Group at CSIRO. Dr. Ali Agar, Principal Investigator and Research Technologist at NASA. And Dr. Sean Humbert, Professor of Mechanical Engineering at University of Colorado Boulder. Audience, we plan to run this session by inviting opening remarks from each panelist to set the scene. Then we're going to expand into a panel discussion with everyone, and that can include you if you wish. Audience, you will notice that Q&A icon at the bottom of the screen. Please add any questions you might have, and we'll hopefully make time to answer a few of them after our speakers. Fast-fingered panelists may even consider typing their answers into the chat as well. Talking of panelists, let's go to our first and setting the scene of subterranean surveilling. Here's Dr. Timothy H. Chung from DARPA. Please, can you turn on your camera and microphone? My goodness, you are ahead of the game already. Are you ready to go?
Absolutely. Very excited to be here.
We're so happy to have you. I'm going to go on mute now, and we'll be enjoying your presentation.
Great. Thank you, everyone. It's a pleasure to be here. And as was mentioned in the introduction, I think it's a really exciting time to be thinking about robotics and the role that they'll play in being able to explore and understand the fascinating world that exists right below our feet. And so one of the ways in which we've been able to help drive this forward is through the DARPA Subterranean Challenge. For those of you who don't know, DARPA is the United States advanced research arm, the Defense Advanced Research Projects Agency, and I have the distinct pleasure of being a program manager there, where we were able to facilitate the DARPA Sub-T Challenge. So just to share a few ideas of how many of the panelists here today are passionate about robots for subterranean exploration, the DARPA Subterranean Challenge helped set the stage. And the intent behind this challenge was to help drive the inspiration and discovery of novel breakthrough robotic technologies that will enable us to better understand this diverse underground environment. And one of the things I wanted to do was just share that in these subterranean environments, there are commonalities between those tunnel-like environments, for example, rescue situations in mining industry, all the way to the urban underground, whether those be subway rails or municipal infrastructure, or even parking garages, all the way to naturally occurring caves, which are all abound everywhere in the world. And so those common characteristics, everything from the challenges of maneuvering in these really tight spaces, all the way to hard to see where you're going, especially when there's no ambient lighting. And then the three-dimensionality of these fantastical underground environments really stretches what you might need to face if you're sending in teams of robots. And so amidst all of those commonalities, you can see kind of on the right-hand side that there's that overlap. But then in each of these subdomains, as we like to call them, there are particular unique attributes that really make that type of an environment particularly hard. And that's what's challenging for us as technologists, as end users, as explorers, to make use of these robotic technologies. And so here are some of the things that we've seen makes the subterranean environments rather difficult, especially for our robotic systems. Everything from the variable lighting that you might either bring with you or that might be available, the fact that driving or flying around in these underground environments might be dusty, or there might be smoke just due to the emergency scenario that you're facing. Of course, water, moisture, things of that nature make it particularly arduous. And then there are other elements of this terrain, whether they be the stairwells or the elevator shafts or other openings that might cause problems. And then, of course, is the unknown dynamic obstacles in these environments. Is the structural integrity sound enough to send in our robots, or will there be ceiling collapses or other things to contend with? And so I'm showing you some photos of the types of environments where DARPA has challenged folks from all around the world to put their robots into these very difficult environments that include things like occluded vision, smoke-filled arenas, vertical shafts and holes in the floor, to many levels of stairwells and so forth. And I've even had the chance to go to many of these sites, such as those naturally occurring caves, and having to crawl on my hands and knees and so forth, and imagining what it would take to have robots go traverse these areas, quite challenging. And so to highlight one of the things in which we're able to accomplish this in the nature of the DARPA Subterranean Challenge, I wanted to further share a little video that highlights how our teams were able to face the challenges that DARPA set forth. There we go. Challenge is about developing and defining the problem, not about defining the solution.
This challenge has the opportunity to create that environment for innovation.
I think that the toughest thing academically about this is having multiple robots work together with very limited human interaction.
You can't just have one thing work, right? You have to have 5 different things simultaneously working. And getting to that point is extremely non-trivial, but I think that that's ultimately the real value.
We love this challenge because it allows us to emphasize on the hardest problems in robotics at the moment, in mobility and autonomy, and emphasize on how to solve them.
We think that the virtual is a chance to showcase ourselves.
Clearly, this is the world top research group, industry group, coming together to solve this unique challenge.
And so to highlight, hopefully that highlights how we've been able to kind of emphasize the development of these robotic technologies. And what I want to end on here is that it doesn't happen in isolation, but in fact requires and benefits from inputs and collaboration from all around the world. like we've been able to demonstrate in the DARPA Sub-T Challenge. And so I really applaud and am excited about this opportunity to engage with the worldwide audience to share some of the lessons that we've learned, as well as offer up ideas and collect ideas for where to go next. So thank you very much, and look forward to the panel discussion.
Thanks very much, Tim. Great. Well, you may be forgiven for thinking NASA only looks up, but of course they're interested in all kinds of exploration. And our next guest, Dr. Ali Agar, Principal Investigator and Research Technologist at NASA, what a title, will tell us more. Please, can you turn on your camera and microphone so that we can hear and see you, Ali? And we are going to get a little bit of a primer about what on earth, literally what on earth, NASA is doing with subterranean robots.
Awesome. Thank you, LJ. Let me see if I can share my screen. Perfect. Okay. Can you see my screen?
We can indeed.
Awesome. Perfect. Thank you very much for introduction. And yeah, Tim, gave an amazing overview of the focus in subterranean exploration. My talk is going to be mostly focused on AI and autonomy and how it complements robotic mobility and robotic systems and helps them to explore subterranean environments. So I'll start maybe with this slide, that why NASA is interested in exploring subsurface voids and subterranean environments. So planetary caves on Mars or pits on Moon, specifically the potential caves on Mars, actually are one of the most likely places to find life in our solar system. Why? Because they have the potential to shield a potential life from effects of radiation, cosmic rays, and extreme temperature variations on the surface. At the same time, they actually are one of the potential shelters for future astronauts for when we have manned missions to these sorts of destinations. So because of those needs, actually caves are one of the most important targets for NASA. And there are, what you see in bottom left video here is a project funded by NASA that basically pushes the technologies and explores how robotic systems can navigate in Mars-like caves on Earth. So this is from Lava Beds National Monument in Oregon, and where you see a legged platform exploring this Mars-like lava tube to demonstrate to NASA that where we are in terms of the technologies, in terms of robotics and AI, and what we can do so that we can take another step towards making this a reality in the next decade or so, and actually have a mission to a subsurface void in beyond Earth. We search for elements like you see, the ones you see in the right, as signs of life or microbial colonies in these environments. And typically these missions are carried out in a multi-robot setting, as you can see on the top right, where multiple robots coordinate to search and sample the environment. But some of the technical challenges we face in exploring Mars-like environments or planetary analog courses are actually pretty common or similar to what we face in terrestrial applications when we are tasked to navigate over a terrain after a disaster, for example, a natural disaster, in search and rescue missions. So what you see on the left here is actually one of our robots trying to explore a collapsed part of a limestone mine. And it basically highlights how autonomy figures out what part of the passage and where the robot can actually, what passage it can choose to be able to go to these collapsed areas. And then when it reaches there, it's looking at its vision, thermal cameras, and different sensors on it to look for potential survivors or targets of interest in that area. To develop these AI and robotic systems, we look at different sorts of metrics, such as coverage, how much a system can cover, how large of environment it can cover, with what speed, what's the endurance of the system. and how intuitive and real-time the communication with the operation crew is. And to improve these metrics, there are different aspects of the technology researchers can push forward. Specifically, two aspects are robot body, building better robots, better mechanical system locomotion systems, as well as better robot brains, better AI, and autonomy for the systems. So I'm gonna advocate for the fact that I believe robot bodies are more advanced than AI at the moment. So even with the current systems, we can enhance and improve our AI solutions to enable better capabilities. So that has been the focus of our team, and we have been trying to develop autonomy solutions that are as agnostic as possible to the mobility platform. Here are some of the mobility platforms that we have integrated our autonomy solution on, ranging from legged robots to wheeled rovers and drones. Typical concept of operation in subterranean missions for us has been sending a team of robots into the environment, and they dispatch themselves to different parts of the course with complementary capabilities. And this concept of operation has been developed and matured under Dr. Chang's DARPA Subterranean challenge that expedited a lot of development for us and helped us to understand much better this problem. So typically in the DARPA Subterranean challenge, what we do is we drop these communication nodes, like blue nodes that you see here, to create a wireless mesh network and talk to the operator on the surface while the system is able to. But as soon as the robots go to a more challenging part of the course, non-line of sight, we lose the communication and the robots are on their own, exploring the environment and coming back to give us the data after their mission is done. The lot of different modules come together to enable these complex behaviors in such challenging environments. Here are a few selected technology areas that I will just touch on, each one very briefly, to just highlight how this integration allows for these behaviors and helps the system to navigate these challenging environments. The first one is on robust navigation, trying to solve where the system is when you do not have GPS, when the environment is potentially dark and dusty. For robust navigation, we rely on a host of sensors. They get fused to each other to help the robotic system to navigate through different challenges and switch between different modalities based on the situation in the environment. Mapping, of course, is another important component of the technology, where the onboard sensors on the robot help the system to create a geometric representation, a 3D model of the environment that in turn later is used to figure out what are the passages and how the system can cover the space, or multiple robots come to rendezvous points and exchange information with each other. Mobile networking and communication between robots. As I mentioned earlier, our system tries to drop communication nodes like breadcrumbs you see in the top left video, and these create a graph and create a wireless mesh network closer to the operator to extend the reach of the human supervisor and operation crew in search and rescue missions. Multi-robot task allocation is an important aspect of exploring these unknown environments. Why? Because they are so complex that typically we do not have a single locomotion system that can handle all the elements of the course. So you need, like a human team, different skill sets, different types of robots that are exploring the environment and understanding which robot can handle what part of the environment, and those decisions are basically fall under this area of research. Machine learning, understanding semantics of the environment and covering the environment is a critical aspect. So typically there are areas of interest in these environments, such as there's a survivor that we are trying to find, and there are different signatures as listed at the bottom here. A radio signal, a sound, a gas, a visual, or a thermal signature. And basically the system needs to understand such semantics and explore and search for those. Here you see the ground robots at the top and drone systems at the bottom that basically are trying to go to different corners and parts of the environment and search for these signatures to find signs of life, either as a survivor or in planetary setting as past life. And finally, traversability, which we touched on earlier, but I would like to share this top left video that shows how resiliency is important in these environments. They're so complex that hard to guarantee a system can survive it. And this video shows some of our attempts in basically try to revive a system after a failure happens. The system falls at part of the environment, tries to recover itself, stand up and continue the mission and go on, which is an important capability to increase the resilience of systems in such challenging environments. So as my last slide, just some high-level thoughts. So search and rescue capabilities, when we analyze them, it's important to look at the integrated robot brain and robot body as the overall solution. And pushing and advancing AI and the robot brain part can make a significant difference even with the current mobility systems. The latest advancements such as DARPA Subterranean Challenge and other projects are actually increasing the trust in these systems, helping them develop the technology, and hopefully will lead to wider deployment. And finally, from the technical perspective, algorithmic perspective, we have learned that due to the complexity of these environments, there are a lot of unexpected events. So it's important that algorithmically systems are ready to predict and quantify risk for off-nominal situations to enable a resilient mission. With that, thank you very much. And I believe we are gonna go back to questions at the end of the talks. Thank you.
Thank you very much, Ali. That was absolutely great. A brilliant presentation from you as well. And now let's explore a little bit further the theme of robots and humans working together with Dr. Sean Humbert from the University of Colorado Boulder. Come in, Sean.
Thank
Have
you,
you switched
LJ.
on your camera? Yes, excellent. This is going very smoothly, isn't it? Are you ready with your presentation?
Absolutely. Thank you, LJ. And thank you to the organizers. And thank you all for joining us either this morning or this evening. So I'll go ahead and share my screen. All right, so my name is Sean Humbert. I'm a professor in the Department of Mechanical Engineering at CU Boulder, and I was the team lead for Marble in the Subterranean Challenge. So I'm going to talk to you about basically how AI-inspired autonomy has evolved throughout the challenge and where we're going in the future. So as Tim hinted to in his movie there that he played, I think a lot of the teams initially at startup in 2018 when the challenge kicked off were focused on one or two or maybe even three of these components. But as the challenge evolved, what really was the most important thing was being able to integrate all these together. And so what I'm going to show you some examples of our team. And what that really sort of amounted to at the end of the competition there was teams of robots really being used as tools to go interrogate subterranean environments. So we saw a lot of autonomous exploration and coordination and some basic human-robot interaction. So again, I'm going to show you a couple quick things from our team with respect to that. But really, most of my comments are going to be high level about where we're going in the future with these sort of things. So our team was composed of a couple different types of robots as well. So we used the legged ones to do a lot of the exploration in sort of the more complicated terrain. We also had some wheeled platforms that were basically comms droppers to extend our comms network. So that was from the mobility side. On the perception side, I think the solution that most teams converged on was sort of an IMU with an LiDAR. So that's all the localization stuff. We ended up using Gigi cameras for all of our artifact detection, and we had some additional flash LiDAR sensors for doing terrain analysis and so forth. And of course, these are dark caverns most of the time, so we had to bring the lights with us with the LEDs there. So our mapping and localization solutions, so our team had competency in visual inertial and radar inertial, but we quickly realized once we started exploring caves and things that visual wasn't quite robust and the radar stuff was a little bit too sparse to do the mapping that we really needed to do. So this is an example, this movie playing on the right, this is one of our spot robots. This is the map that it built and the paths it was planning during the final event. And this is particular as part of the cave situation. So again, we ended up going to more of a LiDAR inertial SLAM solution, and our particular world map was based on an occupancy grid-based 15-centimeter voxel representation. So for us, that was very easy to share maps and merge maps between different agents. And the nice thing about that particular structure also allowed us to do some semantic labeling. So labeling stairs for our spots to go up and down, as well as traversability for all of our other platforms to take a look at. Now, as far as detecting and localizing artifacts, again, here's some of the basic AI stuff. I think a lot of teams were using the Tensor RT solution, which is a deep learning based algorithm that requires a lot of training. We married that to the localization solution you saw there, and we had some additional fusion algorithms that allowed us to predict and localize artifacts and send those back to our human supervisor. Okay, so again, there's just a couple examples of some of the technology demonstrations. Now, our team primarily were autonomy folks, and we looked at the Subterranean Challenge for the most part as an opportunity to go demonstrate some autonomous behaviors. And so the backbone of our team was our autonomy, really focused on that. We wanted to be able to deploy robots and not have the human supervisor even need to interact with them whatsoever. But as we sort of progressed through the challenge, and especially at the final event, I think our team and our solution was robust enough. So we started actually thinking about it as a tool. And that's where I think most teams were. So, they were using their systems of robots as tools to go interrogate those environments. So we saw autonomous exploration and coordination and some basic human robot interaction. And so I just have one quick movie I'll play for you guys there. So these were some of the video streams that were coming into our base station during the final event. You've got the first person views from our 2 spot robots. You notice the top one on the left there that just went out of comms range, so that'll hook back in a second, and transmit its artifacts and its maps and so forth. But again, you kind of see the quality of the first person view that you could get here. And again, thinking of this as a tool, it was such an interesting thing for our team. Like I said, we were really trying to demonstrate different autonomy principles and autonomy solutions. But it was really fun when we got to the point where our system was robust enough to think of it as a tool, right? And that's where the human interaction with the robots came into play. So we could, robots might not have the right autonomy capabilities to push through like smoke and all the interesting curveballs they threw at us in the course. But the human supervisor through top-down reasoning is able to kind of do that instead of the bottom-up reasoning for most of our autonomy, right? And you can see there that robot just connected back, and you can see its pose graph and the map it was adding. But it's really cool because I remember being a graduate student and seeing the movie Minority Report. And in that movie, there's a team of law enforcement looking for Tom Cruise's character in a building, and they send these spider-like robots in there. And this is the kind of map that was popping out on their iPads or whatever their tablets were. But I think it's just great that the DARPA Subterranean Challenge has pushed the technology to the point where we're actually doing that. So that's pretty cool. And kudos to Tim for having the vision to pull the Subterranean Challenge together. Okay, so I'll wrap up with just a few high-level comments on where we're going in the future. Now, again, at this point, we consider those teams of robots to be tools that we can use to interrogate subterranean environments. What needs to happen for them to become teammates? So the first thing, we're thinking about, how do you certify that? And so first of all, what is autonomy and how do we certify it? So usually in these systems, it's very easy to identify the user. It's very easy to identify the machine. But then, what is the autonomy? And so from my perspective, it's really just everything in between. And so when we certify a user, we do that through like a performance-based certification. Like if you get a driver's license, you got to go take a test. So for a machine, you have a process and you build it and you test it and it looks good. Okay, so we can go produce N of those things. But now, how do we actually certify the autonomy piece of this? If we're going to be working with robots as teammates, we need to be able to trust them and so forth. And so, do we use more performance-based certification? Do we do process-based certification? Or do we need to come up with new approaches in order to be able to certify those types of systems? So that's one thing we're thinking about. And again, for robots to be teammates, one of the things that's also important is for them to have some self-confidence. So they need to understand the level of uncertainty of their world model, their state, and then their ability to reason or execute their sort of abilities. Okay? And so I've got a picture of Arnold there. And so, hey, come with me if you want to live kind of thing, right? Do you trust that robot or not, right? That cybernetic organism. So again, trust and trustworthiness, two different things. So a trustworthy robot is something that, may do what you ask it to do or execute a certain behavior. But trust is an entire different thing. That's something that evolves and it's a latent principle. And so it's very difficult to define, and we can spend the next hour trying to argue what trust means. It's even harder to observe and validate. right? So that's something else that we're eventually going to need to be able to do if we want robots to act as teammates. Okay, and then one last quick comment here. So pretty much everything I've showed you, and I think in a lot of the teams that participated in the challenge, all the AI that was being employed was from bottom-up reasoning. So you're using sensors to generate information and build world models, and then you look for expected patterns in those types of things. And so for instance, one very simple example of that is using some depth data in front of the robot to classify whether or not terrain's traversable or not. Okay, and so again, most of these capabilities rely on, traditional machine learning or deep learning types of algorithms, require large amounts of data and sort of lack the causality. So I think what we need, in order to take that next step to have robots as teammates is have top-down reasoning incorporated as well. So what I mean by that is perception that's driven by context. So you want to be able to fill in gaps that the sensory information doesn't have. And so I live in Colorado, so I drive in the snow a lot. If you take a look at that picture in the top right, you and I can look at that very quickly and understand where the driving lanes are. But a robot, so I think the yellow line is barely visible under one of those tire tracks there. They're typically not able to fill in the gaps that the sensor information generates. Right, and so again, there's some advantages here, significant less data than the bottom-up approaches. But again, it's very difficult to actually try to create algorithms like this that function. And how do you certify those, and how do you trust robots that are operating like this? And so one last quick comment before I hand it back. So again, I think in the media, and you hear a lot of machine learning and deep learning type algorithms advertised as being or having capabilities that approach sort of human reasoning. And I want to push back on that a little bit. Again, I think these technologies remain quite limited and they're highly brittle. And what we really need to do is be able to integrate both bottom-up reasoning as well as top-down reasoning. And so with that, I just want to quick shout out to our amazing team and all of our wonderful postdocs and students that supported our effort. And I will hand it back to you.
Brilliant. Thank you very much, Sean. And so thank you also to your human and robot colleagues. As to whether to trust Arnie in Terminator, it really depends on the firmware, doesn't it? Is it Terminator 1 or Terminator 2? Anyhow, great questions coming in. Please put them in the Q&A segment, and we will, I'm sure, get to at least a few of them. My goodness, thank you for your enthusiasm and interactivity. We love it here. All right, it's time for our fourth guest, who will give us even more to digest on system resilience and collaborative teams. Take it away, Dr. Navinder Kotage from CSIRO. Can you please turn on your camera and microphone? Cool avatar, by the way.
Thanks, LJ. I'll share my screen now.
All right, I'll leave you to it.
All right. So yeah, thanks LJ, and thanks for the organizers for having me. It's been some great talks already. So I'm Navinder Kotage. I'm the group leader for CSIRO's Robotics and Autonomous Systems group based in Brisbane, and I was also the team lead for the CSIRO Data 61 team that competed in the Subterranean challenge. So today I will talk a bit about how a heterogeneous robot team with homogeneous sensing helped us achieve a successful outcome using artificial intelligence and collaborative intelligence. That is what Sean touched upon. That is where humans and machines work together. Here, what we're trying to do through collaborative intelligence is to get humans and machines to work together where the sum outcome is far greater than its parts. That is when we harness the best of what humans can do and combine it with what the best of what machines can do. So before I get on with it, I'll give a quick introduction of our organization, the CSIRO. The Commonwealth Scientific and Industrial Research Organization is Australia's premier government-funded research organization with a history of over 100 years. We employ over 5,000 staff members organized into 9 business units spread across 58 sites, mainly in Australia, but also includes overseas locations such as Singapore, Vietnam, Chile, and the US. So CSIRO's research areas are quite broad, and they span agriculture and food, land and water, health and biosecurity, oceans and atmosphere, space and astronomy, minerals, energy, and data science. So as part of Data 61, the business unit that's responsible for data science research, I lead the Robotics and Autonomous Systems group, consisting of 50 staff members and around 40 students and affiliates, so a total of around 90 people. Here are some robots that we have worked with in our group over the past 2 decades. So these span from automated frac lines used in open cut mining weighing over 4,000 tons, autonomous rock breakers, load haul dump trucks used in underground mining, autonomous forklift trucks, autonomous underwater vehicles, autonomous surface crafts, legged robots, uncrewed aerial vehicles of different form factors, and uncrewed ground vehicles of many different varieties. All of these share some things in common. They're all field robots operating in real world environments where we have little to no control over the environmental variables. All right, so now getting on to our Subti Challenge team. So this journey started for us back in 2017 when we responded to a DARPA broad agency announcement. And we were among the few teams that received funding to compete in the challenge, like my colleagues in this webinar. So we had Emerson, a Brisbane-based drone autonomy company that spun out of our lab 3 years ago as one of our subcontractors. And some of you may be familiar with their flagship product, HoverMap. Our other subcontractor was Georgia Tech, based in Atlanta, Georgia. So Emerson provided us with drone autonomy and Georgia Tech provided us with multi-agent coordination capability. Ground robots, SLAM or simultaneous localization and mapping capability, communications and exploration capability came from Cyro. So fast forward 3 years of competition in multiple circuit events, we were selected to compete in the finals among 8 teams. So we faced some additional challenges due to COVID, where we found it difficult to send our core team from Australia over to the US. So here are some images where you see where we had to hire robots to help us deploy robots. So we had to get a bunch of telepresence robots so that our co-engineering team could support the team that we could send over there to do any debugging and help with the maintenance and upkeep of the robot fleet. So I will show you a video of our final prize run and try to explain what happened along the way. I will also try my best to show a few different views of what went on during this run. So what I'm trying to demonstrate here is how overall system resilience was maintained when subsystems started to fail in a harsh Subti environment, where AI and collaborative intelligence played a significant role in maintaining this resilience. And the other thing that I think the other speakers also emphasized was for you to successfully deploy a robot team in a harsh Subti environment. There are many systems that need to work together. The robots themselves need to be robust enough, and your autonomy and your mapping and your communication, all of that needs to work well together. So this view that you'll start seeing is a post-processed rundown of what happened in terms of communication and connectivity between the robots, and then I'll switch to different views. So you'll see a bunch of red dots moving around in the screen, and then it'll become clear as you go as to what they are. So they represent the different robots. So our robot team consisted of 2 tracked robots and 2 quadruped robots and 2 drones. And our ground robots had names. You see some names coming up. So we had Rat and Bear. So they were the tracked robots, and Bluey and Bingo were the legged robots. So I'll play the video and then you'll see. First of all, it was a Bingo, or one of our legged robots, that was sent into the course. And these lines between these red dots are radio connectivity, communication back to the base station. And you might see some light blue nodes, and they are the communication nodes that we dropped along the way to maintain connectivity. And here you'll see that this particular agent that's gone quite deep into the course has lost communication to the base station. So there's no line connecting it back to the base station. So that means the human operator at the base station has no information about what that robot's doing. And here you'll soon see that robot gets disabled there, but our human operator has no knowledge of that because it's beyond communication range. And this is the view that the base station gets, or one of the views that the human operator at the base station sees. So here you can again see the different robots moving around, and you'll see the different artifacts being detected at the base station in different colors. And soon you will see Bingo, this green robot here, goes beyond communication range. And you'll soon see it says comms lost. And then the other robots are going about its business. And then without the knowledge of the human operator, this is what happened to Bingo. And that's how it ended its run, about 20 minutes into the 1 hour. And continuing on, you have another one of our legged robots moving around there. That's beyond comms at this stage as well. So it's happily exploring using our autonomous exploration algorithms, going downstairs. And then for a very brief moment, it makes radio connection to the fallen robot over there. And that's when very briefly the human supervisor gets to see that there's another part of this course over here. And still the score is 12, and then we are more than 30 minutes into the run. And finally, the second legged robot, Bluey, goes to where the fallen robot Bingo is, connects to it, collects all the data that it has, all the valuable artifacts, and tries to bring it back. And this is, again, the view of the human supervisor. So we've scored a number of points, but at this point, our second, one of our track robots, it's disabled again, right here in the middle of the course. And since we're carrying a drone on top of that, so 2 robots are disabled there, and our legged robot. So 3 of our 6 robots are disabled at this point. And then our other legged robot that was trying to bring data back also falls. And at this point, we have 4 of our 6 robots disabled. And we only have 1 track robot carrying a drone that's operational. So that at this point, since the human supervisor knew that there was another part of this course where we potentially have our lost robots, it's trying to desperately send the robot over to collect that valuable data. And here you'll see finally it makes radio connectivity to the fallen robot with very little time, less than a minute. So this is what's happening at the base station. Our human operators are anxiously trying to score the final point. So you'll see the score is 22 with around 30 seconds remaining. And then you'll soon see the final reports coming through as the radio connectivity of that robot gives the data back to the base station, and we score 23 points there. So the end result is we scored 23 points, and then tied with Team Cerberus, which Costas will tell you more about their experience there. But in the end, we managed to get these really beautiful looking maps of the subterranean environment. This is all collected during the final run by our team of robots. So this is, to me, is a great example of how robots failed, but overall the system performed as expected and managed to give us this really valuable information of the subterranean environment. So this is another view of the course where we colorized the point cloud received from our Wildcat SLAM system, and then I'll quickly show you how what the components were for achieving this outcome. So our main competitive advantage was the homogeneous sensing with heterogeneous platforms concept. Each of our ground robots, legged and tracked robots, had the same sensing and autonomy payload, a spinning velodyne lidar that we call our CatPack, and Emerson's hover map on the drones, which with a different form factor. But the same spinning velodyne lidar and was all running Cyro's Wildcat SLAM when that was providing mapping and localization. This slide shows the various different robots that we deployed over the past 3 years, not just the ones deployed in the finals, showing our sensing system can be easily adapted to various heterogeneous platforms. Each of the platforms have the same camera-based perception system using Cyro's DNet object detection framework, and each of the ground platforms have the same autonomy payload running our multi-agent navigation stack. Our multi-robot task allocation system allows the robots to communicate with each other and use an auction-based system to bid for tasks so that each robot could explore different sections of the course without interfering with each other. The overall autonomy allowed beyond comms range exploration when there's poor or no communication back to the base station. And robots can explore beyond comms, collect object detections, and come back to comms range and send the data back to the base station. So our communication system is based on reagent radios, and we have developed a communication framework on top of that for data sharing in a lossy and resource-constrained comms environment. And our Wildcat SLAM is available through Emerson, who licensed this technology from us for HoverMap, and also through AutoMap, who developed a version of our CatPack under license, also running Wildcat SLAM. And these are also examples of how the technology developed during the SAPTI challenge had been kind of pushed out to the community, and now it's commercially available. And another reason for our success is the rigorous testing that we did before we send the robots off to the DARPA finals. So this is showing how our communication nodes were deployed and how our drones were deployed off the back of the ground robots. And this also shows some of the rigorous testing that we did to achieve that outcome. I'll quickly wrap up there and show some videos of the legged robots being tested in our lab as well, where sometimes we were a bit mean to our legged robots. But other than that, I think for us, the really great outcome is the component technologies that we developed here can be used in so many real world applications such as mining and search and rescue. And we are very keen to translate this technology into real world use cases. So with that, I'm happy to answer any further questions during our panel discussion. Thank you.
Navinder, thank you very much indeed. I like that you're presenting from a subterranean background, and you have a subterranean background in terms of what you've done. And those of us who may have watched the acclaimed Australian children's show Bluey may recognise the robot naming convention that you've gone with there. Okay, thank you. Before we start our Q&A though, let's connect everything back to the United Nations Sustainable Development Goals, or SDGs, as you all probably know them as. And we have Dr. Kostas Alexis from the NTNU, who is going to make sense of everything for us. So could you please turn on your camera and microphone? And when you're ready, I'll turn mine off. All good?
Thank you. Thanks a lot. Thanks everyone for attending. And thank you also for organizing this event. So I'm gonna tell you both about why we participate in the competition, but also I'm gonna show some of the technologies that allowed us to participate and win the finals of this competition. So as to start, first of all, just to bring back to the robotics before we go to the applications, I'm going to show a few instances of the winning run where you see 4-legged robots exploring the environment that DARPA presented to all the competitors in the DARPA Subterranean Challenge. And moving a bit beyond that, I would like to invite you to think about the fact of the extreme diversity of underground environments. And I have posted one photo of an underground mine, an urban underground infrastructure, and a natural cave in these 3 images. And the next set of images is also from the same category. It's also an underground mine, an urban subterranean infrastructure, and now an ice cave on the right. And the third set is also from the same type of environments. And what I want to convey with this is that subterranean environments are particularly diverse. And I must confess from my side that before joining the activities of underground robotics and the DARPA Subterranean Challenge, I was not able to understand actually the extreme diversity and interesting aspects of the subterranean worlds, which in fact we can say that they present a trifecta of resources, biological significance, and engineering for diverse activities. And I think my previous colleagues also amplified and discussed for the same. Now, what DARPA achieved and what personally I think all of us appreciate in the competition is that they managed to put all these challenges, the most notable challenges, together in one sequence of competition events, the so-called circuits, and especially the final event, where we had to deal with all the different aspects of these worlds, which we would face if we were to deploy robotics in real-life applications in the underground domain. Robots are already deployed underground. Here we are talking for systems that operate completely autonomously in possibly previously completely unseen subterranean worlds. And that's the interest also, both from an industrial standpoint and also from a scientific standpoint. And indeed, with respect to the Sustainable Development Goals, if we manage to achieve such levels of autonomy for robotic systems in the underground, then we can think, first of all, that we can maximize the safety of critical societal operations. In every major city, we rely on the subway network. Improve the safety of storage of potentially hazardous materials, such as nuclear waste, which is a problem that is existing now, and it will persist due to the nature of the waste. Facilitate safer and more productive work in underground mines, construction sites underground, and more, which means also safer work and better job opportunities for our people. Improve the safety, security, and efficiency of the way we extract resources in a particularly resource-limited world. Reach deep corners of the Earth and other planets, as was commented by Ali and NASA JPL, to conduct valuable scientific campaigns, and overall support the needs of an ever-increasing global population in our times. So accordingly, from our team, motivated by the DARPA Subterranean Challenge, we assembled a team called Cerberus, motivated by, for those of you that know Greek mythology, motivated by the three-headed dog that was supposed to protect the underworld. And our team stands for Collaborative Walking and Flying Robots for Autonomous Exploration in Underground Settings, and corresponds to a broad international collaboration from the University of Nevada, Reno, ETH Zurich, NTNU in Norway, UC Berkeley, University of Oxford, and two companies, Flyability and Sierra Nevada Corporation. So first of all, I must say that we managed to do this collaboration also during coronavirus and this, the severe constraints of our time. But going to the technical, we worked along 5 directions of research, namely versatile robots to facilitate systems that are dexterous, legged and flying robots that can access and interrogate any type of underground environment. Resilient perception through multimodal sensor fusion for localization and mapping in these conditions. Autonomy through unified exploration across legged and flying robots. The ability to not only map, but also detect objects of interest and localize where they are. And an aspect that existed for all teams, which is to facilitate underground networking, which is an important part, which is very difficult to be achieved, however, persistently throughout the underground environment. And I will touch upon each of these main technologies before we connect it back to the applications. So with respect to the robotic systems, we utilized 4 animal sea-legged robots, which you see on the leftmost, and a set of flying robots, with the legged robots being the type of systems that can access with endurance and go deep into the environment and so on and so forth. And the aerial robots being the systems that can go to more difficult vertical type of exploration, but are limited from endurance, which means that in fact the combination of these 2 types of systems is the possible answer to subterranean exploration, alongside only one traditional rover acting with a role of communications extension. The legged systems, of course, had the ability to integrate a lot of sensors, which means that we're able to penetrate all conditions of perceptual degradation, such as smoke, which is a moment that DARPA fills the environment with smoke and challenges the robotic perception capabilities of all the teams, as shown here. But also flying systems, although they had smaller sensing capabilities, they were able to go to difficult environments and also manage to do seamless vertical exploration. Now, as Ali pointed out, the robotic systems themselves is one part of the story. The autonomy algorithms is the other side. And I think perception is now and will continue being one of the most significant challenges. And what we try to do in our team and many other teams in the Subterranean Challenge is to facilitate multimodal perception as the answer to the challenge of diverse degradation, being smoke, dust, self-similar, or simply the matter of extreme scale. You think of, for example, the network of the subway of London, which is, spans across multiple kilometers. The answer to that for us was that we will combine different sensors, such as cameras, lidars, thermal cameras, and so on and so forth, alongside proprioception, such as inertial sensors, to have an estimate of the robot location and the map that is robust at any moment. And beyond that, as was also shown, for example, from Navida, was the combination of mapping capabilities of different robots to bring together one global map, effectively delivered to the operator and for any type of mission requirement. And if mapping is one aspect, the second major aspect of autonomy is autonomous planning and guiding the robot and the team of robots in these complex subterranean environments. To that end, from our side, we worked on complete autonomy at the level of a single robot, with the human operator only defining by drawing, essentially in a seamless manner, what is the area to be explored by a single robot. However, at the level of a team of robots, we wanted the human to be there because we strongly believe that still up to now, high-level reasoning and understanding about what are the most profitable directions for exploration for these robotic teams is not necessarily possible with full autonomy. So with some level of high-level semi-supervision from a human, we're able to reach robust exploration of underground environments using the heterogeneous team of legged and flying robots. Now, I would like to show some results to understand how things work essentially in practice. This is one of our last field campaigns before moving to Kentucky for the finals of the DARPA Challenge. And what you see here is the animal robot exploring an underground mine. And the pink paths that you see on the right is the self-decision of the system about where to go based on the current map that it reconstructs from the environment. And this will continue. And it's notable that the method will be scalable across kilometers of exploration. Also locally, it has to make very expensive calculations. And this works for legacy systems. It will allow to come back to the home location as it is required for to get the data if there is a loss of communication, or to go back at least to communication point. It's the same thing for flying robots, regardless of size. If they are very small, such as the robot that you see here, which can go fast into and also access very constrained environments. And similarly, it is possible for robots, flying robots also, that are more equipped with respect to sensing, here integrating thermal vision, to cope with the visual degradation introduced by the dust in the environment. It's interesting from the fact that our team was in different places of the world, the United States and West Side in Nevada, Norway, the United Kingdom, and Switzerland. And we also had the capability to access different types of underground environments implicitly through the fact that we're geographically distributed. And our experiences, I started this work when I was in Nevada. Our experience there was very different from the experience of our colleagues in Switzerland, very different from what we faced afterwards in Norway, and very different from our colleagues in the UK. Nonetheless, knowing the diversity is a prior to make more robust and more resilient systems and algorithms. If we put these things together in the final run of the DARPA Subterranean Challenge, we managed to put our team, and what you see here is the trajectories from each of the 4 main legged robots that accessed the environment in final runs and managed to acquire our score and by mapping the environment and detecting objects of interest. So these are the trajectories by each robot. And if we take now the trajectories, we remove them and focus on the map and annotate where we identified objects of interest. What you see here is the top view that you will get also from the robots as they explore the environment in real time. And I think currently what I'm going to say, it's not possible, strictly speaking, but the vision is that this should be like a video game, effectively, where someone who is not necessarily a robot expert, we've had robot experts from our side for this team because that's the nature still of research. But eventually, what the goal of the Subterranean Challenge is that we deliver technologies that can be seamlessly used by those that care for the mission and the end result without necessarily being roboticists themselves. And so the high-level goal is that we will deliver this map for people, and they should be able to understand and possibly interfere with where the robot should go to explore better and deeper in this underground environment. So this is the result of our winning run. Before I close, I want to credit all the members of my team and of course all the collaborators and competitors, but in fact colleagues throughout the competition. I want to credit everyone that helped us in winning the competition, and in order to support not only scientific development and growth, but also consolidation and to support industrial adoption of these technologies, a significant aspect of our work related to open sourcing. And hopefully, by releasing technologies to the general public and possible industry, these technologies can be used more quickly in practice, and therefore support the goals of economic growth, sustainable development, and so on and so forth, as introduced in the beginning. With that, I want to thank you, and I'm just playing the last moments of our winning run in the DARPA Challenge. I think the video will continue, so we don't have to watch it all. I can just go towards the end. But just for
oh no, LJ here, we can see the triumphant bit at the end.
Yeah, that's 23 points. It's exactly the same as Cesare's and Amanda mentioned. We literally had a few seconds of difference, and that was the tiebreaker. It doesn't matter. At the end, what matters is the technology. But we are happy, all of us participating in the DARPA Challenge, and for us, we're happy for winning the first place.
Thank you so much. And thank you for all those videos. My goodness, it's been awesome. What a great opening. And I can see all of your questions, audience, as well. It's absolutely wonderful to see all of those. So I'm going to invite all our panelists to turn on video and audio for the Q&A section. And I will strongly encourage you all to talk to each other as well as me. And we're going to start with me asking a few questions. And then as and when audience questions, I can sort of grab them and try and ask as many of those as we can. But first, I'm going to start with Tim. You've been nice and quiet throughout this time, very patient. Although I suspect you might all have an answer to this question, so feel free to jump in after him. If there was one future component, so like a sensor, an actuator, a radio, faster processor, anything that you wish you could have today, what would make the most difference? Tim, we'll start with you.
Oh, thanks, LJ. And this is a question I can't wait to hear our other panelists also contribute their answers to as well. I'd say one of the amazing things here is that we've seen robot platforms do really well. There's still some work to be done there. I think miniaturization and productization, hardening in these really challenging moisture-ridden, dust-filled type environments is going to play a role. I do think that maybe some new sensors are probably just around the corner, just waiting for us to take advantage of. And so I do think that there might be some breakthroughs right there that will help us go through smoke, dust, maybe even see through some of these walls or some of the terrain, and help us image what's around the corner and things like that. So that's one of the places I would love to be able to see right around the corner without having to put my robots in those dangerous places.
Brilliant, thank you. Does anyone else have anything they want to add to the wish list?
I can comment.
Sure.
I think the first point is exactly sensing. But if I had to pick one ultimate combination of things, I would like to have the technology, sensing an algorithm that will make sure that my robot, if the terrain is traversable, it manages to traverse it. And if the obstacle can be avoided, it manages to avoid it. So we used to call it obstacle avoidance. Now it's more about not only about obstacles, but also terrain. So it's this combination for me of sensing that's richer, but also from that going to the representation that allows the robot to avoid and manage to find its way through a very complex environment.
Do you know, I think it would be brilliant to bring Ali in on this AI versus mobility. Do we need better robots or better robot brains? I guess this is mechanical versus electrical. I don't know. Would you like to expound upon this?
Sure, yeah. I think an interesting way of looking at maybe that question is thinking about if we give these robots to a human with a joystick, what can they do, right? And I believe many of the robots we are using in this competition or other subterranean exploration, if you give the joystick and the robot to a person, that person can do much better than what we can do today with AI with them, right? And if you think about it, that person doesn't really have much better sensors or prior about the information. In fact, robot sensors are better. They can measure distance that we cannot with a high accuracy and things. But it is really that decision making, like something that Sean also mentioned, like human looks at the terrain and they understand much more of the semantics and context in the scene, which we yet are not able to do. So I believe, of course, developing of mobility and mechanical part would help a lot, as we can see different robots can do better at different parts of the course. But the much bigger challenge that the community, as a community, we have to solve or push further is on the robot brain to make it closer to what a human can do with joystick with these robots.
I think it's a good idea to bring Sean in here as well, because in terms of reaching human parity, human reasoning, where do you think we're going? Do we have a timescale when AI-based systems are going to have that capability? Do we want them to think like humans or just better?
Yeah, that's a great question. So yeah, I second Ali's comments. I think having some of that top-down reasoning would be great. I think in recent developments, there's been a hybrid. So, humans use both bottom-up and top-down to do their analysis. So I think, some recent research has been pushing on that front. Looks very promising, but I still would say we're 10 to 15 years out from some of that stuff. But if I was going to ask for a component, I would certainly want some level of top-down reasoning available to my robot to be able to reason across the environment and the world model that's building. I also second Costa's comments. I think one of the hardest parts of this competition was doing the terrain analysis and understanding when your robots can traverse and when they can't. I think we went in with a pretty conservative approach, but we rectified that with the human supervisor able to push the robots through certain areas that the autonomy wasn't able to get. But I definitely think that was one of the harder parts of the competition.
I think when you encourage humans to have some part in the supervisory process, it does tend to have quite an effect on the quality of the output. And I can say this from my experience as a music composer. If you just let the AI go off and do something on its own, most of the time, it isn't something that humans would enjoy listening to for more than maybe 10 seconds of novelty. So it sort of makes sense when you start involving machines. In fact, I'm going to ask Navinda, how can we apply these technologies through the Sub-T challenge? How do we apply this to the real world? Because obviously we're looking at the SDGs in our AI for Good series. So where do you think this sort of technology is going to end up?
As it was mentioned in the previous talks, I think we had to have so many subcomponents or sub-technologies working together for us to get this outcome. So my belief is that even if we don't apply all of them together for certain real world applications and scenarios, there definitely will be applicability to for various subcomponents. And I'm going by the experience from our team, and I'm pretty sure it'll be similar for other teams as well. It's different subcomponents at different levels of maturity. Certain things were far more advanced than others. So the things that were that are more advanced and much more robust can readily be applied to real world scenarios, such as our SLAM technology, which I mentioned in my talk. We are already commercializing it. We are already licensing it. So people can buy it as a product, and we already know that this is being used in real world scenarios where people are using it in almost on a day-to-day basis for mapping underground environments and then mapping various infrastructure, even applied to heritage protection and preservation, where they're using it to create accurate 3D maps of ancient archaeological sites and things like that. The next one that we are trying to push out into the hands of end users is our multi-agent navigation stack, where we believe that it can have a lot of benefit in not just search and rescue, but also things like biodiversity surveys in a rainforest and that sort of scenarios where you definitely would benefit from having a team of robots going and exploring and being able to detect your biodiversity. So I believe it'll be a gradual process as different components become more mature. They would have real world applicability, and then you can use them in conjunction with different parts. And I think the beauty of this is, given the different teams, we might have different components that are at higher levels of maturity. So once all of this is advanced, an end user might be able to use one component developed by our team, combined with another component developed by Costa's team, and then Sean's team, and then Ali's team. And I think that's the true beauty of it, where people can kind of pick and choose which component to apply in their real world applications.
Brilliant. Thank you. Costas, I'm going to bring you in because I bet you've got some thoughts on which technologies need to mature so that this does get adopted on a wide industrial or commercial basis. Feel free to wax lyrical.
Yeah. So I think, first of all, the ladder that Navinda mentioned, the mapping, first of all, and the navigation technology is something that currently it's already being deployed into industry with significant success. And we see, for example, for underground mines, that this is, and people inside this webinar are working with companies to make sure that these technologies already find their way. However, from my perspective, if it was about making subterranean robotics used ubiquitously across all types of applications in the underground world, controlled or not controlled environments, safe or unsafe settings, I believe that what we call perception as a human is different than what we achieve as reliable perception in robotics. So we are at the level of having very robust maps. I think all teams, Navinder's team, demonstrated first of all that you can have very, very good maps from the underground world. However, overall understanding, what is it that I'm seeing? Where should I go to collect more information? And so on and so forth. This is far away from being established in what we call mature robotics research. So I think what we are missing is a reliable pair of eyes that do not only perceive, but also analyze the context of their scene. And I think research-wise, the keyword for that is spatial AI. So we move away from just vision to spatial representations of the environment that encode intelligence. And luckily, a lot of people are working for that across the world. And hopefully we will see this in the hand of industrial companies and so on and so forth soon in the future.
I remember many years ago being introduced to a robot that had been built to solve the Rubik's Cube, but the problem was the machine vision had difficulty distinguishing between the red and the orange faces in certain kinds of light, and otherwise it was able to run the program, but the recognition bit. So it does feel like there's always a spot of difficulty. Talking of spots, we do have a question all about dirt, actually. This is from Ehsan. Can you share with us your experience with excessive dust as well as moisture in this kind of environment? Did your vision sensors get affected? How did you handle this issue? Recently, the Perseverance on Mars had to deal with getting a bit too many pebbles in its sensors, didn't it? And I think it just stopped and asked for further instructions. When you think that's like 334 million kilometers away and it knows what to do. So let's talk a little bit about this and maybe widen it out to what happens when you get stuck. Who fancies answering that first?
Yeah, I can jump in. So, yeah, a lot of our aerial vehicles with the dust, they of course stir up all the dust in the mines. And so the vision inertial slam didn't work well at all. It continuously failed. I think with LiDAR inertial, even with the dust and the smoke, that sensor can't quite penetrate that. One way around that is radar. And that's why our team kind of focused on radar at the outset. We didn't quite get it to prime time and we didn't deploy it in the final competition, but it's almost there. So I think part of the problem was the sparseness of radar compared to LiDAR. So we couldn't quite get the mapping data. But I think that sensory modality is something that would really help when it comes to smoke and dust and particulates and things like that.
Tim, I can see you nodding there.
Yeah, absolutely. I think one of the things that we found when we engaged with those first responders, that the hardest things for them to have to send in their people was because they couldn't see what was right in front of them. And so dust, smoke, in fact, for the DARPA Subterranean Challenge courses, we were filling some of the segments with that theatrical smoke just to make sure that teams could stress test their technologies. One of the really interesting things that Sean mentioned was that not just the smoke that might be there due to the emergency or the smoke from the fire, but also the dust that you kick up as you're driving or crawling or flying or falling in these environments. And so there were strategies to try to outrun the dust that you're kicking up. There were strategies to let it settle after you've kind of moved to an area. So understanding that. The other really interesting thing was that there are so many different types of dust. It depends on the particulates or the color of the smoke, and that changes all of the sensing modalities that are effective in those regimes as well. And so finding those capabilities that can perceive the environment, even if it means kind of walking with your hand along the wall, like we might do in the dark or in the dusty environments. Are there novel ways that we might think about employing our robots to deal with not having eye vision, but other ways to navigate the environment?
Brilliant. Thank you very much. I'm just going through the fantastic amount of questions that you've sent in, audience. We love it. We've got one question here from Dr. Rakesh. What are big challenges in tunneling robots in mining? Now, is this something that anyone deals with, or are you all legs and wheels? I think I get the impression that tunneling might not be part of it, because I know that animal can go on 2 legs or 4 legs or wheels, which is a slightly different thing to actually drilling down. I think this is about mapping. So I'm just going to move on to another question here. We've got quite a few. I've already
I just want to say for the latter
yes.
that
go ahead.
I just want to say the distinction. We were asked not to interact with the environment. Team can confirm that it was part of the rule. I think when you also add the component of interaction, so tunneling means that you're actually trying to change the environment. This is a host of extra challenges, and it will take another gathering of big teams to make sure to address also. So I think the question, I just want to say that if we're talking for big machines, maybe it gets simplified, supposedly to make it happen. But if we're talking for smaller machines or sending in space for asteroid mining and things like this, this is a very hard challenge.
Brilliant, thank you. Sean, I'm going to ask about field testing, certification, validation. When you're dealing with complex systems, this isn't just sort of press a button and let it go. It appears to have so many different inputs, so many decision points. How can you deal with surprise theatrical smoke, for example? What do you do when you're field testing?
So that's a great question. In order to deploy a system that actually works and is robust at this level of complexity, you've got to get out there and test it. You've got to figure out the corner cases and everything. And we learned this the hard way throughout the challenge. And again, I commend Tim and his team for putting together a sequence of events. We went through all these circuit events before the final event, where we got to deploy our robots in each of the subdomains and really kind of iron out all the kinks and things. But even when you do that, like, you've got to get out and you've got to practice and you got to do that. If you don't, you're just going to hit all the corner cases, as we did in the urban case. We advanced the complexity of our system quite a bit, and then next thing you know, we couldn't even get the robots out of the gate. But again, I think most of the teams learned that lesson early on and were able to deploy just really resilient and robust solutions. So it was just awesome to see, as soon as the clock hit 0, like, the first robots were going in for each of the teams.
Wow, brilliant.
I would like to second Sean's comment there, test and more testing. So we did a lot of integration testing where we tested the whole system together. We did individual component testing, but we did very regular integrated team testing. So we try to follow the paradigm of test as you run and run as you test. So that helped us quite a bit.
Yes, it feels like you have to break things quite a lot before you can get it to work. Ali, how do you balance something like speed with something like endurance? Where do you find that balance?
Yeah, interesting question. It's really hard, specifically if you do not have prior about the environment, right? If you have some knowledge how the environment would look like, you can find the sweet spot. But I think our team, and I believe most of the teams, kind of try to address this challenge by introducing a team of robots that were ready to be deployed depending on what the other robots are learning, the kind of scouting robots are learning about the course. So you have systems like drones that are really fast, but very minimal endurance. They can fly a few minutes, but they can really fly fast and do certain things like go grab a data from a robot that is broken and cannot recover, or you have the wheel platforms that are a lot of endurance, big batteries, and can carry a lot of payload, but pretty limited to surfaces that they can go. They cannot go over stairs or very challenging environments. And then you have legged platforms, kind of in between. They have higher endurance than drones, but lower payload capability than the wheeled robots. So I think having that team of robots and being able to have algorithms that decide, oh, I see stairs, legged robot, go here. I need endurance here. It's a very long corridor, but it's flat, and the wheeled platform is an essential part of this, and still as an open area. We scratch the surface on this competition, but I think a lot more to be done on that front.
Mm-hmm. I have a question for everyone now. How do you overcome latency in the system? Do you see what I did there? Because obviously connectivity is a big deal. I know it was pretty bad, but I'm really glad I did it anyway. So let's have a little talk about that, because obviously connectivity is an issue, especially in subterranean environments. How how are you solving that problem? Is there anything you think would help? And yeah, could we talk a little bit about that?
I can jump in first. So what we did, our approach was to endow each of the individual robots with as much autonomy as possible, where they can still function without any connectivity back to a base station. So our paradigm was the human supervisor gives very high level mission goals to each of the robots and send them into the course without any expectation that they'll be able to maintain communication with the robot. So once they go in, once they have that high level mission, the robots had enough autonomy to do their task, which in our case was exploration. So we had an exploration algorithm which kind of incentivized the robot to go look for things that it hadn't seen before. So it was a frontier-based exploration algorithm. So each of the robots had their own missions, and then we could allocate tasks. And then on top of that, we had a multi-robot task allocation system where even if they couldn't talk back to the base station, if they could talk to each other within the course, then they could negotiate which tasks which robot does. So having that sort of local autonomy for each of the robots allowed us to kind of get away from any of the detrimental effects of latency. So that was our team's approach.
Brilliant. Thank you very much. I've got a question for Sean. Based on your testing, which had a better and accurate outcome, LiDAR SLAM or radar SLAM? Can you address the major challenges between the two? Well, you've only got a few minutes, but do your best to answer a massive question.
Yeah, no, it's a really interesting question. I think, based on the solution that most teams support, the LiDAR-based solution is much better, right? So you're looking at successive point clouds to correct the drift in the IMU, essentially. Now, so LiDAR is great. Yeah, it's very dense, a lot of points, great for building the maps too. But also smoke and fog and things like this confuse it, right? And so that was one of the complications. And I think, several of us ran into those instances in the final competition. So radar can go through that stuff. And so it can sort of penetrate those types of smoke fields and things, get the information from the walls, and you can still build like a LiDAR or like a SLAM solution off that. The problem with radar though is that it's sparse, right? So it's not as dense. And the points move around. There's a bit of uncertainty with the points as well. And based off the geometry and the shapes of things in the environment, that also it reflects differently, and you've got multipath, so you've got a lot of issues to deal with there. But I think that the place where it's really going to come into effect is for smaller air vehicles. So it's really difficult to carry those, $10,000, like, 20 or 250 kilo, or whatever, the LiDAR. Those are pretty heavy solutions to carry around, really detriment in terms of payload and flight time for the UAVs. But the LiDAR solutions are credit card size, very lightweight types of sensors. And so we've got those systems working to the point where we can do localization and odometry. It's almost as good as the LiDAR solution, but not quite.
Brilliant. Thank you very much. Wow, we're coming to the end of our time together. And I like to end these panels with a question to everyone where they get to choose. You get to choose which question to answer now. So it's a little bit of control back to the panel, a control panel, if you will. So what one thing would you like to change? That's one question you can answer. What challenge are you proud of meeting? Let's discount the Subterranean challenge out of that, because obviously you must be very proud of that. And finally, what would you like to do next? Those are your three questions that you get to choose from. And I'm going to go with Costas first for that. So what one thing would you like to change? What challenge are you proud of meeting? And what would you like to do next? You can answer any or all of those.
Yeah, I'll start with the latter, and I'll pick the first one too. So with respect to what's going to happen next, I think the general direction of what we try to do is to penetrate any type of confined environment. And confined environments go beyond what was shown in the videos here today. And humans enter manholes for 50 meters to enter another inaccessible area. So we need robots that are resilient to all conditions. And in particular, for that, there is an interplay of what we traditionally robotics call perception and action loop. And so far, we designed these modules that you saw today, mapping, planning, control independently. The only way for resilience is if this AI or autonomy algorithms, however you want to call them, are co-designed in one comprehensive, risk-aware fashion. With respect to the question of one thing that I will change, I think, so I think I will change in the competition the ability to modify the environment. If this was an option, I understand this would be an extra DARPA challenge, but or what is called DARPA hard problem. But if in another point there was a similar competition and we're able to modify the environment, you will see current robots failing miserably because suddenly you will also have to open a door, but also extreme innovation coming into the game. So this is something we're trying to explore in our future research too.
Brilliant. Thank you, Costas. Okay, Tim, you're up next. What would you like to change, or what challenge are you proud of meeting, or what would you like to do next?
Sure. I think one of the biggest things that I'm most proud of is the fact that you see these panelists and all of the competitors really coming together as a community. There was a lot of collaboration happening, and I think a testament to that is the type of data sharing or the data sets, the open source code, the collegiality of everyone. I think what that speaks to is that it really does require the best minds from all around the world to come together to tackle some of those sustainable development goals. For example, the UN SDGs, just like the subterranean world really does require the world to come together to do that. And so I'm really proud and really excited to have seen these best minds come together, tackle some of these hard problems, find different ways to solve these problems. And now from this common reference point, we can move forward and have mutual understanding over and respect of all the possibilities that are out there. I think for the future, I'd say, and it's really, really bright. And I say that despite being underground, I'd say the potential for technology breakthroughs, we're absolutely at that cusp where breakthroughs are turning into commercial products, turning into things that end users can make use of. So really excited to see where that all goes. Thank you.
Oh, thanks, Tim. That makes all of us excited. Brilliant. Navinda, you're up next.
Yeah, thanks, LJ. So in terms of what I would change in the context of this competition, I probably wouldn't change anything. I think things are quite well designed in terms of the competition, and in terms of something that we're proud of. We look at our testing videos from 3 years ago. It's like looking at baby photos, and then the level of maturity that we've achieved in our technology over the last 3 years, I think it has been brilliant, and we are really proud of where we've got. And in terms of what we want to do in the future, it's more along this collaborative intelligence piece where for a human and a machine to work well together, something that's currently missing is more context about some of the autonomous decisions the robot is making and being able to communicate that back to the human. That's something that we are currently working on and would like to develop. For example, if a robot at a T intersection, if a robot using the AI decides to go left instead of right, right now the human supervisor doesn't really know why that decision was made by the robot. So if something goes wrong, if that knowledge is there for the human supervisor, they can easily intervene and do corrective actions. So right now we don't have that capability to kind of communicate back why those autonomous decisions were made in such a way back to the human supervisor. So that's something that we'd like to work on and improve in the future.
To peek inside the black box of AI. Brilliant. Thanks very much, Navinda. Ali, over to you.
Sure. Yeah, I think what I'm proud of is similar to what Navinda mentioned. I think when I look back at 3 years ago, we had like 1 or 2 robots, exploring the environment. I'm really proud that our team, in the course of 3 years, at the end, we were able to operate 11 robots simultaneously, 4-legged, 4-wheel, 3 drones. That was just incredible to see all 11 go into the course and in our practice runs and see them how they operate. In terms of future, I would say a few things. One, I would, Kostas already mentioned this, but traversability analysis, understanding where is traversable, where is not, I think is a really still a big open problem for the community. Context, understanding the context of the environment and making more human-like decisions, higher level decisions is another aspect. And I would say the third big item I would love to see the community pushes forward is understanding the health of the system, right? When different components start getting degraded, either being perception, locomotion, or due to the environmental effect of robot, how do we understand that, manage it, and fold it back into the decision making?
Brilliant. Thank you very much, Ali. Finally, Sean, a nice quick one for you, please.
Sure, yeah, super quick. I'm just so proud of all the undergrad, graduate students, and postdocs, not just on my team, but across all the teams. So if we think about the DARPA Subterranean Challenge, Tim mentioned a lot of the technical impacts and advances we made. I personally think the most important and the largest impact is going to be the students that go out and start the new companies and that become the next generation of academic leaders. I'm just so excited for these folks that are coming out right now. And if you're looking to hire some good students, like, you know, come talk to us, because we've got some amazing talented kids coming out.
Wow. Well, thank you. And what a note to end on. Thank you so much, panelists and audience. It's been a real pleasure to host this session. And I am sure everyone here would welcome contact for further ideas and projects. This is just the start of the discussion, by the way. So if you are watching and thinking, hang on, I can contribute to this, don't wait. Simply get in touch with our panelists. And thank you again for having me. It's time for me now to say thank you and goodbye and hand back over to Guillem to close the session. Thank you.
Thank you very much, LJ, and a big thanks to our panelists, Navinda, Ali, Kostas, Sean, and Timothy, as well to all the participants for making it such an interesting discussion. We had lots of great questions and amazing insights into the technologies and challenges for deploying robots into underground environments to tackle the UN SDGs. We are now opening a quick poll with one question. Please answer and let us know how much you like this session. We also encourage you to check out the AI for Good program online to see more sessions that may be of interest to you. For example, on February the 17th, we'll have an AI for Good robotic session on wind industry, green energy robots for achieving the net zero future. On Thursday, the 3rd of March, we will have a session on cobots for good, the future of human-robot collaboration. And finally, on March the 17th, we will be discovering how robots are getting a human sense of touch. With that, we have reached the end of this webinar, and we would like once again to thank everyone involved, our panel, our participants, our partners, sponsors, and co-convener Switzerland. Thank you very much, and hope to see you again soon.
Selector, rewind selector, rewind selector. Rewind selector, rewind selector, rewind selector. Selector, rewind selector, rewind selector. Rewind selector, rewind selector, rewind selector. Selector, rewind selector, rewind selector. Rewind selector. Rewind selector. Rewind selector.